Okay. Give me a while. Okay, so many assembly language instructions alter flag register bits, right? And some instruction function differently based on the information in the. So what is about the flag register? So flag is the status register. Okay, so it is a 16-bit register. Okay, although it is 16-bit wide, only some of the bits are used. Okay, the rest of that are either undefined or by Intel. All right, so it is mostly used in the Intel microprocessor. Okay, for example, we have this. So we have 6 flags called condition flags, indicate some condition resulting after an instruction executes. For example, so we have 16-bit, right? So we have from 0 up to 15 bit, right? So we have allocated, right? We have allocated instruction inside this flag register. So for example, so the upper 4 bits, for example, from 12 to 15, right, location. So reserve it, all right? So we reserve it, okay? And then, okay, let's start from the bit 0. So at the bit 1, at number 0, so we have CF, which is the carry flag, okay? And then we have undefined. So you see that there is a space allocated after each of the instruction. For example, we have at location number 1, we have undefined, 3 also undefined, and 5 also undefined. Okay, so TF carry flag, TF is parity flag for number 2. For number 4, it is auxiliary carry flag, okay, AF. And then we have ZF 0 flag. Okay, and then between 6 and 7, we have no more undefined, so we just continue. So with the sign flag, number 7, and number 8 with the trap flag. Okay, and number 9, interrupt flag, direction flag, overflow flag. Okay, so that's the maximum of the flags that we use. Okay, so this is called as the conditional flags. Okay, so because actually we will do actually flagging, okay, after we perform some calculation. Okay, so this is the conditional flag. All right, so the sixth one, okay, the overflow flag, sign flag, 0 flag, auxiliary carry flag, parity flag, and carry flag are the conditional flags. Okay, the remaining 3, so this blue one. Okay, so for this blue one, so which is the direction flag, interrupt flag, and trap flag, are called the control flag. So this is a control, and all of this and this one, okay, are the conditional flag. Okay, conditional. All right. So what's the difference between conditional and control? So the control are operation of instructions before they are executed, but condition after instructions executed. Okay, so that's the difference between conditional and uh, control flag. Okay, so the flag bits used in the 86 assembly language programming. So we have CF. So what is CF? CF is when they carry out from D7 after the 8-bit operation, or D15 after 16-bit operation. Okay, so this is like whenever you have the maximum, all right, the maximum instruction, all right. Let's say you already have for D7, you have already F. So you have D7 to D0. So that's already maximum from 0 So you have all F. Then there is an additional information, so you need to put that into the carry flag. So similar for the 16-bit. So where you have the full of that is already filled with the 16 instruction, all right, or 16 code, then you need to put the additional information to the carry flag. Okay, so it is also used to detect errors in unassigned arithmetic operations. Okay, all right, so we also have the parity flag. So for the parity flag, after certain operations, the parity of the results low order byte is checked. Okay, so this is after some operation. Okay, if the byte has an even number of ones, the parity flag is set to, otherwise it is clear. Okay, so it is checked whether it is an even number. All right, if it is an even number, then the parity flag is set to 0. So otherwise, other than that, it will be clear. Okay, so we will for the example after this. Right, so the auxiliary carry flag, if there is a carry from D to D4, for example, right? So otherwise, it is cleared. Okay, so this is for D3 to D4 only. Okay, so that's related with the auxiliary carry flag. So this is used by instruction that perform the BCD, which is the binary coded decimal arithmetic. Okay, we will look for the example after this. Okay, we just go through with the explanation of this flag first. Okay, so set to 1, for the 0 flag, we have set to 1 if the result of the arithmetic or operation is 0, otherwise it is cleared. Okay, so if the result is 0, so it is different from the what we have here, the parity flag. Okay, parity flag will be 1 when we have even number, but when we have 0, so we have the 0 flag as 1. All right, we also have sign flag. So sign flag is for binary representation of signed numbers, uses the most significant bit as the sign bit. Okay, after arithmetic or logic operations, the sign bit is copied into the SF. Okay, so it means that the status of the sign bit is copied to the SF, whether it is actually it depends on the significant numbers used as in the instruction. Okay, all right, and also we have the thread flag. So the thread flag is set allows the program to single step, meaning to execute one instruction at a time. Okay, so single stepping is used for debugging purposes. Okay, we also have interrupt enable flag, IF. So this bit is set to clear to enable or disable only in external maskable interrupt requests. Okay, we will look for the example to this. Okay, so we also have DF, the direction flag used to control the direction of string operation. And we also have overflow flag, where it is set when the result of a signed number of operations is too large, causing a high order of bit to overflow into the signed bit. Okay, used only to detect errors in signed arithmetic operation. Okay, so now we look at the example. So the flag bits affected by the add instruction. So this is for the addition instruction. So what is affected? So CF, PF, AF, okay, ZF, SF, and OF. These are the flags that that are affected. Okay, when we do the add instruction. Okay, for example, all right. So we look at the example 110. So we have show how the flag register is affected by the addition of 38 and 2F. Okay, so first we move 38 to BH, right? So now BH becomes 38, and then we add 2F to the BH, and now BH becomes 67. All right, so in terms of Okay, so this is in terms of hex. Okay. Okay, let's also look into the binary. Okay, so 38 is converted to binary. We will have this one. Okay, so we have this number. All right, and 2F converted to this one. All right, so we have that number, right? So you still remember, right, on how to convert that? So 8, so of course we expand this into 4. All right, this 3 also into 4. Okay, when F, of course, it will be 1, 1, 1, 1. So this is 2 to uh, all right. So we have of 0, okay, 2 to 0, 2 to 3. Okay, so that's why we have here as 1 for 8 and 0, 0, 0. All right, and we have 1 here, 2 to 0, 2 to 1, so it's 3. Okay, here you have 0, 0, 1, 0, which is equivalent to 2, and 1, 1, 1, 1, which is equivalent to F. All right, so we perform the addition. Okay, when we perform the addition, so we get 1, 1, 1, and 0, 0. So 1 uh, will be carried out. Okay, will be carried out. Okay, and then when we have 1 and 1 here, so we have 1, 1 plus 0, it will be 1, 0, right? So it becomes 0 and 1. So 1, 1, 1, and also become 1, 1, right? So 1, 1, 1. Okay, and 0 is 0. Okay, so we look here. How it affects the flag. Okay, so we look at D7. See, carry flag affects at D7. So 0, 1, 2, 3, 4, 5, 6, 7. So it is 0 here. Okay, so when it is 0, so the carry flag will also be 0. Okay, so AF, the auxiliary carry flag, it is 1. Because why? So we look at here. Okay, from this is D3 to D4. Okay, so here from D3, so this is D3, and here is D4. Okay, we just saw that we need to carry 1, right, to D4. So that's why AF now becomes 1. Okay, so it is meaning from 1 byte to another 1 byte. Okay, so from D3 to D4. And PF is 0. Okay, why PF is 0? Because there is an odd number of ones in the result. Okay, so because there is an odd number of 1, what is odd number? So even, okay, odd and even. So even is what we call 0 to 4, right? 0 to 4, 6, 8. Okay, but here PF is 0 when there is odd number of 1 in the result. Okay, so you look here, so we have 1 here and also 1 there. Okay, so that's why we have 1. All right, that's why we have PF is 0. If here it is 0 and also here it is 0, so PF will become 1. Okay, and ZF is 0 since the result is not 0. Okay, and SF, the sign flag, at D7. So we look here at D7. So here is D7. The result is 0. So SF is 0. Okay, so that's how the flag. Okay, That's how the flag reacts to the addition. Okay, so let's say we have another one. All right, so let's say we do the addition. All right, so first we move, right? So we move 9C to AL and 64 to DH. So you look here, all right? So you look here that this is the high 4 bit, and then this is another low 4 bit. So this is an 8 bit, right? So this is an 8 bit operation. So 8 and 8. Okay, so what we have here, so we look that, so we have 9C is added to 64, where the DH is added to AL, which is 64 is added to 9C. Okay, and then you look that because this operation gives you what, right? It gives you 0, right? Okay, so we look that, so when we add C to 4, so what we have when we have C, okay, A is 10, B is 11, C is 13, okay, 10, 11, sorry, 10, 11, 12, so C is 12, okay, 12 add with 4, so you obtain 16, right? So when 16 minus 16, so you got 0, and you add 1 here. Okay, so this is what I mentioned. Right, so you have 10 plus 16, also you get 0. Okay, so actually we have another 1 here, but it won't be shown there. All right, so the result. Okay, so when you convert that to binary, it will become like that. Okay, so because we have 1 beyond this 7, so that's why our carry flag will become 1. Okay, so we look also over here, 0, 0, 0, 0, 1, 1 will be 1, 0, right? So we add 1, 1, 0, so it will become 1, 0. So there will be 1 carry over from D3 to D4. So AF is also 1. Okay, so PF will become 1 here now because there is an even number of ones in the result. Okay, so there is even number. So let's say here, so we look at, so this is even number. Okay, so we have the parity of 1. Okay, so because we have the even number of 1 in the result. Okay, although you mentioned here this is a 0, okay, but because of we look that it is an even number of ones here, all right, so we have that SPF as 1. Okay, so compare back to here, so we have this as this is, as this is an even number, this one odd number. Okay, that will be odd number. All right, so this is odd number. Okay, so that's why you got PF as 0 there, and then here PF as 1. Okay, and ZF, of course, because the result is 0, so we get ZF equals to 1. And we look at, for SF, we look at D7, still 0 because the result is 0. Okay. Alright, so it is important to note the difference between 8 and 16-bit operations in terms of impact on the flag bits. Okay, so the parity bit only counts the lower 8 bits of the result and is set accordingly. Okay, so let's look at example 112. So how the flag register is affected. Okay, so we look here that we have, okay, also the addition. So now we add the 16-bit number. Before this, we add only 8-bit number. All right, so now it will be expanded to 16 binary. Okay. All right. So we look here. Okay. So we look here that what is affected only about the parity bit. So parity bit here is 0. Okay. Because okay. So it is on the even number. Okay. So we look here. And then we also look here. All right. So we don't look at the 8-bit. Okay, so we look at the lower 8-bit. So that is affecting the PF. Okay, for others, it will be still similar. All right. So SF, we look at the highest, D15. Okay. CF, we also look at the D15. Okay. And then AF, we still look at the D3 to D4. Okay. So we have 1, okay, 1101 should be 110 will be 10, so 110 will be okay. So that's why we have AF is 1. Okay, so for 16, so CF and SF we look at D15. Okay, all right, and also the PF we look at the lower byte. Okay, meaning that at this area only. Okay, so for the carry flag is set if there is a carry beyond bit 15. All right, so this is what I just mentioned. Okay, so we look here, right, we have another one. So here, carry flag will become 0. So this is, okay, this should be 8, 5, 5, 5, 6, all right? So we have actually additional carry over here, okay? So what happened here? So we have 10, right? A is 10, 10 plus 6, 16 minus 16 will become 0. So we have 1 here, so it's still 16, so become 1 here, and also 16 become 1 here. Okay, and then we have another 1 actually over here. So CF of course, is 1, and SF will be 0, right? AF, so we look over here. Do we have 1 over here? Do we have 1 from here to there? Yes. Okay, so we look here. So 0, 0 and 1, 1 become 1, 0 and 1, 1, 0. So become 1, 0. Okay, 1, 1, 0. So 1 become 1, 0. So 1 is added to here. Okay. And also PF 1. Okay, because now we see that have that even number, it will become 1. Right? So you assume that if all zeros, of course, it is here. So you see that PF is 1. All right? And ZF, so ZF is also 1. Okay, so let's say we have another one. All right, over here, we have, okay, addition of BX to AX, and then we add AX to DX, and then DX added to CX. Okay, so we have one step, second step, and third step. Okay, so for the addition. So after adding all of that, so we have as C700. Okay, so does this exceed? No, it's, so we have C over here. Okay, but we look over here, binary one. Okay, whether it exceed, we have additional one over here or not. Okay, yes or no. So we look here, so we have, okay, 0, 0, 1, 1, 0, so become 1, 0, and then 1, 1, become 1, 0, also 1, 0. Okay, so of course our AF will be 1. Okay, and then PF, also we look over here that all zeros, so we have PF also 1. Okay, ZF is not 0 because the result is not 0. Okay, and SF, we look over here, A become 1 because the result at here is 1. Okay, we continue with the addition to determine our CF. So 1, 1 become 1, 0. Okay, also 1, 0, 1, 0. And also we have another one here. So 1, okay, so we have 1 plus 0, so become 1. Now carry over here. So 1, okay, 1 and 0, okay. And then now 1, 1, 0 become 1, okay. 1 plus 1 become 1, 0, and become 1, 0. And then here will become 1, 0. Sorry, there is no 0, okay. So because this is only 1 and 0, 0, so becomes only 1, okay. Now carry over here, so 1 plus 0 will become 1, okay. Okay, so remember that when we have the move instruction over here, okay, it does not affect any flag, okay, because it just move. Only when we perform the addition, okay, when we perform the addition, then it will flag. All right. So because we just move, when we move, we just move the value. We don't perform any arithmetic operation. So that's why flag is not affected. Okay, widely used application for of the flag register is the use of the zero flag to implement program loops. Okay, so a loop is a set of instruction repeated for a number of times. Okay, for example, we want to add 5 bytes to the of data. A counter can be used to keep track on how many times the loop needs to be repeated. Okay, so each time the addition is performed, the counter is decremented and the zero flag is checked. Okay, so when the counter becomes 0, okay, the zero flag is set to Z, F equals to 1, and the loop is stopped. Okay, so we look here. So let's say first we move the CX, post the loop count, so CX now becomes 05, okay, and then PX holds the offset data address, okay, let's say it's 0200, okay, then we need initialize AL 00, okay, and then BX, so meaning that we add BX over there, so we add the next byte to AL, okay, so BX is added to AL, okay, so and then INC increment, so INC is increment BX, so we increase the data pointer to 1, right? So when we move the data counter to 1, so it becomes 0201, okay, and then decrement CX. We decrease the CX to 1, so CX now become 4, okay, and then J and Z. So jump to the next iteration if the counter not 0. So that is jump instruction. Okay, so we jump to the next counter not 0. Okay. All right, so this is for the 16. So CX and also BX. Okay. All right, over here. So in each iteration, ZF is checked by the jump to the next iteration if not 0. Okay. Jump stands for jump not 0. Meaning that if ZF is 0, it jumps to the new address. Okay. Is ZF is 1, meaning that all of that are 0, so the jump is not performed and the instruction below will be executed. Okay. Okay, so the J and Z instruction must come immediately after the instructions that decrement CX. Okay, so J and Z needs to check the effect of the decrement CX on ZF. Okay, so if any instruction were placed between them, then that instruction might affect the zero flag. Okay, alright. So this is how we call the zero flag is instructed. So it's according to J and Z. So when J is not affected, alright, if J and Z is not affected, like over here, so ZF is 0. But if J and Z, okay, is affected, okay, so the jump is not performed, then ZF will becomes 1. Okay. Alright, the CPU can, okay, so that is about the flag. Alright, so that is about the flag. Okay, the CPU can access operands in various ways called addressing modes. Okay, so now we are entering the addressing modes. Okay, so the number of addressing modes is determined when the microprocessor is designed and cannot be changed. Okay, the x86 processor provides 7 distinct addressing modes. Okay, for example, we have one register, okay, one second as immediate. Okay, so this is addressing modes that is available within the x86 microprocessor. So we have 7. Okay, direct, register, indirect, base relative, index relative, and base index relative. So that's all 7 of the addressing modes. Okay, so register addressing modes involve of the use of registers to hold the data to be manipulated. And the memory is not accessed, so it is relatively fast. Okay, for example, we have addressing modes here. So we have moved DX to BX, okay, and then we move AX to BS, okay, and then we add the contents of BH into the contents of AL. Okay, so the source and destination registers must match in size. So coding of AX to CL, of course, give you an error because AX is 16-bit and CL is 8-bit. Okay, and in immediate addressing mode, the name implies the instruction is assembled. The operand comes immediately after the opcode. Okay, so the mode can be used to load information into any register except the segment and flag registers. Okay, for example, we have this 2550 is added to AX. Okay, so now AX becomes 2550 and 625 is moved to CX. Now CX becomes 5. Okay, and 40 is moved to BL. Okay. Okay, so meaning that this mode can be used to load information into any of register except the segment and flag register. So as long as it's not the segment and flag register, it is okay to load the information. Okay, so all of these are the general purpose registers, so we can upload the information to that. Okay, to move information to the segment registers, the data must first be moved to a general purpose register, then to the segment register. Okay, so this is what we already learned before. Okay, so we must first move into the general purpose register first before we move to the data segment or the segment register. Okay, so this is illegal, so this is correct. Okay, so we also have the direct addressing mode. So what we have before, so we already have register, immediate, and also now it's the direct addressing mode. So in direct addressing mode, the data is in some memory location. So in the most programs, the data to be processed is often in some memory location outside the CPU. Okay, so the data mostly are inside the memory location. So we need to access that. Okay, so how to access it? So we must go through the address bus. Okay, so the address of the data in memory comes immediately after the instruction. So we must have the address of the data. Okay, so the address of the operand is provided with the instruction as an offset address. So we need to calculate the physical address by shifting left the DS register and adding it to the offset. For example, we have 2400 as the part of the logical address. All right, so we have 2400 move to the right part of the DS. So we will be on the lower bit of the DS. Okay. So we move the content. Okay, we move this content from the DS. So this is what we extract from the, move that to the DL. Okay. So that is the direct addressing mode. Okay. So this is the addressing mode. So we have the bracket. So we don't use like before. So we don't use like this. So we don't use AX. Okay. So if we use here is just a value. So we don't take the data inside that address. Okay. So here is we do addressing. Okay. So when we put the bracket, so that's why we do the addressing. Okay, so if the bracket is absent, so as I said, so the command will give an error, okay, as it is interpreted to move the value 2400, okay, into register DL. Okay, so the value of 2400 will be moved to DL instead of the value inside the address of DS2400. Okay. Okay, so what is in register indirect addressing mode? So the address of the memory location where the operand resides is held by register. The register used for this purpose are SI, DI, and BX. Okay, if if these three registers are used as pointer, they must be combined with BS in order to generate the 20-bit physical address. Okay. So let's say we have this indirect. Okay, so we have in the bracket, it should be actually we need to look into the location of data segment of at BX. Okay, we notice that now BX in the bracket. So how to do that? So how the microprocessor perform to read that instruction? So the physical address is calculated by shifting the S left one hex position and adding BX to it. Okay, so need to add BX. First, the S need to shift. Okay, shift left one hex position and add BX to it. Okay, the same rules apply when using register SI or DI. Okay, so here we move the content of DS CI into CL. Okay, and then here we move the content of AH into DSDI. Okay. Okay, so we look at the example. Assume that we have DS, all right, 1120 and SIS 2498 and AX S17FE. Show the contents of memory locations after the execution of move SI, okay, AX. Okay. So this is our AX. Okay. And then what is our SI? So this is our SI. So of course, this one is actually DS double dot SI, right? Okay, so AX is moved to memory location with the logical address this one and DS plus SI plus 1. Okay, so DS plus SI shifted to the left. Okay, so you remember that the physical address of this, okay, this physical address of this will become, okay, initially it is 11200, right? Okay, and then 2498. Okay, so we will from that, we add that, so it becomes 8, 9, 6, 3, 1. Okay, so the S shifted left. Okay, so becomes that. So it becomes 13698. Okay. So according to the little endian convention, the low address, okay, contains FE. Okay. Okay, so the low byte and the high address, okay, the low address contains FE, and okay, this one, this contains this one. And the high address, okay, will contain 17. All right. Okay, in the high byte. All right. So now how it becomes? So we move AX now. So this move will, okay, so will affect this one, okay, at the lower bit. Okay, at the lower 4 bit. So this one will become FE at the low byte. Okay, and then the at the high address, okay, because we need to shift, right? So we need to shift 1, okay, for the high one. So before this, it will become 13698. And after we shift 1, okay, the SI plus 1, okay, it is at 13699. Okay, now will contain 17, okay, in the high byte. Okay. All right, I think I will stop here for today. I will try to give you more example of this. Okay, so we will continue on Tuesday. All right, so we'll finish this until the addressing modes. Okay, so for your test one, it will be covered until this chapter. All right, so your test one will be on Thursday. Right, so this similar time as this during your class time. Okay, from 4 to 5. Okay, so it will be from 4 to 5. Okay, any question?
Next week, Doctor.
Yes,
Next week.
yes, next week. So next week, the date is 22nd. 22nd of April.
Ada spot question tak, Doktor?
Spot question. So the question, I will give you some assignments, alright? I will give you some assignments, so you do the assignments. So actually, it is like what you learn, so you need to know how to, let's say, like this question on how to find out the memory locations, alright? So you are given certain certain set of numbers, alright, and then you need to perform some moving instruction or adding instruction, okay, and see what is that, and then you also need to know what is flag register is used, okay, so the function of the registers. Okay, I will give that as assignments first, and then you see. So actually, it will be lying around that area. Okay, for the test.
Doctor,
Yes.
tak boleh do buat V6 because I already have 2 tests on that day, Doctor.
Kenapa?
I already have 2 tests on that day.
Okay, then
Then can you postpone to week 6? Would. I mean would. Everyone would. I want to do in week 6 because I already have two tests on that day.
how about others? Others have problem to do that on Thursday. How about others? Have you got tests on week 6?
We got test on week 6 also.
You have tests on week 6 as well?
Yes.
Yes.
So it need to depends on the majority of you. So I cannot be based on only one person. So I can do the test, right?
And you do the voting, sir.
It's not possible to do the test only for you, all right? So it depends on the majority. So
Okay.
majority of you agree to do that in week 5, okay, next week, okay, then it is okay. Or do you want to shift that to Friday?
Friday is okay.
Okay.
What time on Friday that you think is available?
After Zuhur.
No, okay, because we go to Jumaat.
Yes, it cannot be after Zohor because it's Friday prayer. So it can be a bit later, let's say at 3 or 3:30.
InsyaAllah, Doktor.
Doctor, at night also can, doctor.
At night because it's Ramadan
Okay.
month. So maybe you can do that, but very late if you want that. Maybe starting at 10 and finish at 11. I'm not sure. If you agree, then it's okay. How about Friday morning at 11?
Yes.
I have class, Doktor.
From 9 to 12. We got class.
We got class.
Okay, so I think majority I think better we stick at during the class time. Okay, during the class time at on Thursday.
Okay, okay.
Okay, doctor.
Right, so it'll be from 4 to 5. All right.
Okay, doctor.
All right, so we'll make it from 4 to 5 next week. All right, so before we finish, so let's take attendance. So please turn on your camera. Okay, camera number 1. Okay, so I count on friend 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Cheers. Okay. One more shot. Hold on, one more shot. Okay, thank you everyone. Okay,
Thank you,
have a,
Doktor.
all right.
Thank you, doctor.
Thank you, doctor.
Thank you,
I
doctor.
see you
Doctor.
again on Tuesday. All right.
Okay.
Thank you, doctor.
Assalamualaikum and bye bye.
Waalaikumsalam, doktor. Selamat buka.
Selamat buka.